That suggests that this is an area. You know, 4 pi r squared is the area of a sphere, the lateral area. So he said, oh, what is happening here, take the same thing here, okay. When you have the field, it's like if you are dividing the total charge by the area. So it's like if you multiply, you can do it here, you can do it here. If you multiply the field by 4 pi r squared and leave on the other side whatever remains. Remember, instead of k, I put 1 over 4 pi epsilon 0. So on the other side, you're going to have the source and the epsilon 0. That's Gauss' law. The integral of E by the area around is equal to the total charge. So now, instead of a point charge, it's the total charge because we are integrating. Supposedly we are doing this here and here and here. And everywhere the field is perpendicular because that's symmetric. So you have to know that. So you can take this out of the integral because it's a constant, and the integral of 4 pi r dr is just the area again. So he said that when you multiply the E by A, you get the total charge enclosed divided by epsilon 0. That's it. So a nice way to find an A on a charge that they distributed on an area is this. Do the integral. No, we never do the integral because we always select a symmetry where the E is constant. Then the integral of the area is the area. So we go back to Coulomb's law. So the field is, well, we put it with 4 pi epsilon 0 r squared and the total charge in here. That's what he's doing. Okay, he creates a fictitious area in which the area is 4. If you use this area, then you put 4 pi r squared of this. If you use the surface of the sphere, then you have to put r squared of the sphere. So you can calculate the field exactly at the sphere. You can calculate the field away from the sphere. Okay? And the formula is identical to the point charge. Look, the field of a point charge is the charge divided by r squared. Except that now the charge is not a point, it's spread. And that's it. So, remarkably, the field of a point of a distribution of charges is identical as if all the charges were at the center. Because it gives you the same formula, the same format, okay? With a bonus, with a plus, with something that we learn now. What is the field here? Well, do the same thing, create a Gaussian surface. What is the charge enclosed? 0. Therefore, the field is 0. Oh, so inside a conductor, the field is always 0. That's nice to know. Because that's the shielding. That's how we shield things. You want to shield equipment from electrostatic field, from thunder, from lightning, put a casing of metal around. It's called Faraday cage. Okay? So you have in your hand the capability to find the field of any distribution of charges. And this is also good for any shape. Eh? The mathematics will prove a peanut, whatever. So without even doing the integral, you can calculate the electric field of a distribution of charges, provided you always keep this in mind. The charge enclosed by that area, okay, it's a closed integral, which we never do, but you have to think of it. You have to create your own Gaussian surface so that the field is perpendicular to the surface. How many cases of this Gauss's law has he taught you? Because yesterday the girls that came, apparently they were lost. And I see that the problem towards the problem, he did apply this. I'm going to erase something, right? He applied it. The applications are typical to the sphere, which is simple. So the field of the sphere is Q. You can put KQ over R squared or simply KQ over 4 pi epsilon 0. Okay. the next application is the field of a rod of charges, which I don't know if he mentioned. What is the field here? Or here, whatever. The same thing. You create a Gaussian surface, which is like a cylinder embracing that rod. Okay? And you know that the field is always away, 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 away. So the integral of this field, the E goes out. So you just have the field by the area of the cylinder, which is 2 pi r by the length of this, let's call it small l. That has to be equal to the total charge in that rod divided by epsilon 0. Okay? And the total charge, when it's homogeneously distributed, can be very easily expressed as the charge per unit length, lambda. In other words, lambda is charge per unit length per L. So, and of course, you can do this an integration. This is the Q, the L. When you integrate, the total charge is lambda L. So, you can put here for the total charge lambda L over epsilon 0. The L's cancel, and then the field of a rod at any point around it is going to be lambda, the charge per unit length, divided by epsilon 0, or 2 pi r epsilon 0. It's another formula. You see, the field decreases as 1 over r. For a point charge, as 1 over r squared. For a sphere, 1 over r squared. But now, when the distribution is linear, it's only 1 over r. And finally, the most important case is apply Gauss's law to a plate, to an infinite plate. An infinite plate is simply this, okay? A metal that is loaded with electricity. Homogeneously, if it's not homogeneous, we're in trouble. You have to do the integration, whatever. But if it's homogeneous, then what is the field of this plane here? What is the Gaussian surface? The Gaussian surface is a pillbox. Here's the surface, and then you construct like a little cylinder like that. Okay. So the integration of the field is just on this side. Well, actually, the field is perpendicular because this is supposed to be very big. So all the field lines go parallel, 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 away from the charges, right? So they come here, here, homogeneously distributed. Also goes down, okay? No, you will see that we don't worry too much about this. Yeah, the field goes down. So, what is the field? The field, Gauss says, is when you integrate this by the area of the Gaussian surface. This is the Gaussian surface. There's no field on this side because the field is parallel. It's only here. So it's the area of this top is pi r square, r square. Yeah. And that has to be equal to the total charge enclosed on that area divided by epsilon 0. Okay. That's it. So the field is, well, divided by 2 because half the field goes up. In other words, the area is twice. Let me put 2 here. So E is going to be Q over 2 pi r squared epsilon 0. And then this guy, like we had a lambda, which is lambda is charge per unit length, we create the idea of charge per unit area, which is called sigma. Charge per unit area. The area here is pi r squared, it's a circle. So we can write the field as simply sigma divided by 2 epsilon 0. Okay? That's the field of an infinite plate at any distance. You see that the r disappears. Okay? So, because it's the area, it's not the distance. So how nice. The sphere is 1 over r squared. The rod is 1 over r. And the plane has no r. The dimensions simplify. When you have two such planes, I'm going to put it on an edge, infinite plane, but now it could be finite, and the other one is negatively charged, you form what is called a parallel plate capacitor. Then the field doesn't go up, doesn't escape, it goes down, down, down. You know, you put a test charge here, it's repelled by the plus and attracted by the minus. So when you have a homogeneous field, the lines are parallel and equally spaced. There's some escape here. Yeah, there's what they call fringe effects, but we ignore that. So the formula is approximate because there's going to be some lines that escape. So what is the field? The same as this one, but since we have this and that, in other words, it flips down. So instead of the area, it's just the area. So the field in a parallel plate capacitor is simply the sigma divided by epsilon zero. How simple. If you want to put Q over A, okay, the area of the plates. So the total Q divided by the area of the plates, and that's it. The distance doesn't count, like here it doesn't count. So you have three formulas using Gauss's law. Field of a sphere, field of a rod, and field of a parallel plate capacitor. Question: do you need those formulas for the test? Do you know? Have you done problem? Because